A black hole is a region of space where gravity is so strong that nothing, not even light, can escape from it. According to the theory of general relativity, which describes how gravity works, a black hole is formed when a very massive object collapses into a point of zero volume and infinite density, called a singularity. This can happen when a massive star runs out of fuel and explodes as a supernova, leaving behind a dense core that cannot support itself against gravity. The singularity is surrounded by a boundary called the event horizon, which marks the point of no return for anything that crosses it. The size of the event horizon depends on the mass of the black hole. The more mass a black hole has, the larger its event horizon is. Black holes are very fascinating and mysterious objects in the universe. They have many strange and extreme properties, such as warping space and time, slowing down time, stretching matter, and emitting radiation. Scientists have observed many types of black holes, such as stellar black holes, supermassive black holes, and primordial black holes. They have also detected gravitational waves, which are ripples in space and time caused by the collision of two black holes or other massive objects. Black holes are still being studied and explored by astronomers and physicists who want to understand more about their nature and origin. Black holes are fascinating objects that have intrigued scientists and the public for decades. They are regions of space where gravity is so strong that nothing, not even light, can escape. But how do black holes form, and what happens inside them? Let me explain the concept of the event horizon and the singularity in black holes. The event horizon is the spherical outer boundary of a black hole, loosely considered to be its surface. It is the point where the gravitational influence of the black hole becomes so great that not even light can escape it. Anything that crosses the event horizon is doomed to fall into the black hole, and can never come back or communicate with the outside world. The event horizon acts as a one-way barrier that shields us from the unknown physics near the singularity. The singularity is the point at the center of the black hole, where all of its mass is concentrated. It is a region of infinite density and curvature, where the laws of physics as we currently know them break down. We do not know what happens at the singularity, or if it even makes sense to talk about it. Some theories suggest that there may be a way to avoid or escape the singularity, such as through a wormhole or another universe, but these are highly speculative and not well understood. The size and shape of the event horizon depend on the mass, charge, and spin of the black hole. The simplest type of black hole is a Schwarzschild black hole, which has no charge or spin. Its event horizon has a radius equal to its Schwarzschild radius, which is proportional to its mass. For example, a black hole with the mass of our Sun would have an event horizon with a radius of about 3 kilometers. A more realistic type of black hole is a Kerr black hole, which has spin but no charge. Its event horizon is slightly flattened at the poles and bulged at the equator due to its rotation. A Kerr black hole also has an inner event horizon and an ergosphere, which are regions where space and time are twisted by the black hole's spin. There are three main types of black holes: primordial, stellar, and supermassive. Primordial black holes are the smallest and most mysterious type of black holes. They are thought to have formed in the early universe, when density fluctuations caused some regions of space to collapse under their own gravity. Primordial black holes could have a wide range of masses, from less than a gram to thousands of times the mass of the Sun. However, they have not been detected yet, and their existence is still hypothetical. Stellar black holes are the most common type of black holes. They are formed by the death of massive stars that explode as supernovas. The core of the star collapses into a point of infinite density and zero volume, called a singularity, surrounded by an event horizon. The event horizon is the boundary beyond which nothing can escape the black hole's gravity. The size of the event horizon depends on the mass of the black hole. For example, a black hole with 10 times the mass of the Sun would have an event horizon radius of about 30 kilometers. Stellar black holes can grow by accreting matter from nearby stars or by merging with other black holes. Supermassive black holes are the largest and most powerful type of black holes. They are found at the centers of most galaxies, including our own Milky Way. They have masses ranging from millions to billions of times the mass of the Sun. And their event horizons can span millions of kilometers. Supermassive black holes are believed to have formed from the collapse of huge gas clouds or from the merger of many smaller black holes in the early universe. They can influence the evolution of their host galaxies by emitting powerful jets of radiation and matter. Here are some of the properties and characteristics of black holes. Mass. The mass of a black hole is the amount of matter that it contains. It is usually measured in solar masses, which is the mass of the Sun. The mass of a black hole determines its size, temperature, and gravitational influence. The more massive a black hole is, the larger its event horizon, the point of no return for anything falling into it, the lower its temperature. And the stronger its gravity. Black holes can have a wide range of masses, from a few times that of the Sun, stellar black holes, to billions of times that of the Sun, supermassive black holes. Size. The size of a black hole is usually defined by its Schwarzschild radius, which is the radius of its event horizon. The Schwarzschild radius is proportional to the mass of the black hole, so the more massive a black hole is, the larger its Schwarzschild radius. For example, a black hole with a mass of 10 m would have a Schwarzschild radius of about 30 kilometers, 18.6 miles, while a black hole with a mass of 10 billion m would have a Schwarzschild radius of about 30 billion kilometers, 18.6 billion miles, too. However, the actual shape and structure of a black hole may be more complex than a simple sphere, depending on its spin and charge. Spin. The spin of a black hole is the measure of how fast it rotates around its axis. It is usually expressed as a dimensionless number between 0 and 1, where 0 means no spin and 1 means maximal spin. The spin of a black hole affects its shape, as a spinning black hole is flattened at the poles and bulged at the equator. It also affects its gravitational field, as a spinning black hole drags the surrounding spacetime with it, creating a phenomenon called frame dragging. Additionally, the spin of a black hole determines how much energy and angular momentum it can extract from matter falling into it, through processes such as the Penrose mechanism and the Blandford's-Najek mechanism. Charge. The charge of a black hole is the measure of how much electric charge it carries. It is usually expressed in coulombs, which is the unit of electric charge. The charge of a black hole affects its electric field, as a charged black hole creates an electric potential difference between its poles and its equator. It also affects its interaction with other charged particles and fields, such as electromagnetic radiation and plasma. However, most black holes are expected to have very little or no charge, as they tend to neutralize themselves by attracting opposite charges from their surroundings. Temperature. The temperature of a black hole is the measure of how much thermal radiation it emits. It is usually expressed in kelvins, which is the unit of thermodynamic temperature. The temperature of a black hole is inversely proportional to its mass, so the smaller a black hole is, the hotter it is. For example, a black hole with a mass of 10 m would have a temperature of about 0.00006 kelvins, while a black hole with a mass of 10 billion m would have a temperature of about 0.000000006 kelvins. However, these temperatures are extremely low compared to other cosmic objects, and are practically undetectable by current instruments. The temperature of a black hole also depends on its spin and charge, as they affect how much energy it can radiate. Entropy. The entropy of a black hole is the measure of how much disorder or randomness it contains. It is usually expressed in joules per Kelvin, which is the unit of entropy. The entropy of a black hole is proportional to its surface area, so the larger a black hole is, the more entropy it has. For example, a black hole with a mass of 10 m would have an entropy of about 10 to the power of 77 joules per Kelvin. While a black hole with a mass of 10 billion m would have an entropy of about 10 to the power of 91 joules per Kelvin, these values are extremely high compared to other cosmic objects, and imply that black holes are among the most disordered systems in nature. The entropy of a black hole also depends on its spin and charge, as they affect how much information. Interesting phenomena associated with black holes. Accretion disks. These are disks of gas, dust, and other matter that orbit around a black hole and gradually spiral inward due to the gravitational attraction of the black hole. As the matter falls in, it heats up and emits radiation across the electromagnetic spectrum, from radio waves to X-rays. Accretion disks are often the brightest sources of radiation in the universe. Quasars. These are extremely luminous active galactic nuclei, AGN, powered by supermassive black holes at the centers of galaxies. Quasars emit enormous amounts of energy, sometimes outshining their host galaxies, and can be seen from billions of light-years away. Quasars are thought to be a stage in the evolution of some galaxies, when they are undergoing intense star formation and accretion. Jets. These are narrow beams of plasma and particles that are ejected from the poles of some black holes at very high speeds, close to the speed of light. Jets are produced by the interaction of the black hole's rotation, magnetic field, and accretion disk. Jets can extend for millions of light-years and affect the surrounding intergalactic medium. Jets are also observed in other types of AGN, such as blazars and radio galaxies. Gravitational lensing. This is an effect of general relativity, where the gravity of a massive object bends the light from a distant source as it passes by. This can cause the source to appear distorted, magnified, or multiplied in the observer's view. Gravitational lensing can be used to study the properties of both the lensing object and the background source. For example, gravitational lensing by galaxy clusters can reveal the presence of dark matter and distant galaxies. Hawking radiation. This is a theoretical phenomenon where black holes emit thermal radiation due to quantum effects near the event horizon. Hawking radiation implies that black holes have a finite temperature and entropy, and that they can lose mass and evaporate over time. Hawking radiation is very faint and has not been detected experimentally, but it has important implications for black hole thermodynamics and quantum gravity. Tidal forces. These are forces that arise from the difference in gravity between 2 points on a body due to another body's gravitational field. Tidal forces can cause a body to deform or stretch along the line towards the center of mass of the other body. For example, tidal forces from the Moon and the Sun cause tides on Earth's oceans and solid surface. Tidal forces also play a role in the formation and evolution of planetary systems, stars, and black holes. If an object gets too close to a black hole, it will experience extreme tidal forces that can tear it apart in a process called spaghettification. Hope you enjoyed this video. Please subscribe our channel to learn more scientific facts.